Dear students, welcome to this digital lecture series. Today we are going to see a very interesting topic in physics, that is relativity, and in that we are going to see the Galilean transformations. Now, in space, suppose that we are having a particle at a particular point. How can we give the information of that particle in the space? Of course, to describe that particle, we should know its position with respect to certain fixed point, and in many cases this fixed point is origin. Also, we should know the time at which that particle was present at that point. So the position coordinates and the time coordinate can satisfactorily explain or describe a particle or an event at a point in a space. So, if we want to find the position of a particle, then we require certain reference. So this reference, in many cases you might have seen that this reference is taken as the coordinate axes. The most familiar coordinate axis for you is the x, y and z axis, which are mutually perpendicular to each other. So, we define a frame of reference, any system of coordinate axis in which any particle or an event can be represented by the position coordinate, and the time coordinate is called the frame of reference. The frame of reference, it acts as a reference from which you determine the position of a particular point where the particle is present or where the event has taken place. Now there are two types of frame of reference. The first one is inertial frame of reference and the second one is the non-inertial frame of reference. So first we will see what are the inertial frame of references. Any frame of reference in which the Newton's first and the second law of motion are obeyed is called the inertial frame of reference. Now what are the characteristics of inertial frame? So generally they are stationary frames. They are stationary, means not moving, and in many cases they are non-accelerated frame of reference. What are the example? Any stationary frame which we know, it can be called a inertial frame of reference. So any stationary frame which is fixed on a body, it is an inertial frame. Or a certain stationary frame somewhere far away in the space, it can also be called an inertial frame of reference. Next is the non-inertial frame of reference. So any frame of reference in which the Newton's laws of motion are not obeyed are called the non-inertial frame of reference. So what are the characteristics of these non-inertial frames? They are generally moving or accelerated frame of reference. And as an example, all the moving frame of references are non-inertial in nature. Now suppose that there are two frame of references. If we denote one by S and another by S dash, and there is a particle or a point where there is a particle or an event has taken place. Then the coordinate of this particle in one frame of reference, it may be exactly different from the coordinate for this particle in the another frame of reference. Now, can we relate the coordinates for the particle in one frame of reference to the coordinate of the particle in another frame of reference? So there are certain equations, certain relations which are helpful in relating the coordinates in one frame of reference to the another frame of reference. So any equation that give the relation between the coordinates in one frame of reference to the coordinate in another frame of reference, they are called the transformation equations. And the first transformation equation which we are going to see are the Galilean transformations. So observe this figure. Now there are two frame of references. One which is shown in black. I have shown only just two axes here, x and y. The third axis z can be somewhere perpendicular along this direction. So consider two frame of references, S, and another frame of reference is S dash. Now let the frame of reference S dash, it is moving with a constant velocity v along the x-axis. The frame S dash is moving with a constant velocity v along the x-axis. Now suppose that there is a point P in the space, and if you want to describe this point P with reference to the frame of reference S, then its position coordinates will be x, y, z, and the time coordinate will be t. Now what will be the position and time coordinate in frame of reference S dash? It will be x dash, y dash, z dash. These are the position coordinate, and t dash, this is the time coordinate. Now these two coordinates are different. Now see what happens. Now the origin at time t is equal to t dash is equal to 0. The origin of these two frame of reference S and S dash, they are coinciding, they are overlapping. This point is exactly on top of this. Now after time t, the frame of reference S dash, it moves with constant velocity v along x-axis. Then after time t, S dash frame has moved a distance vt. Velocity into time is equal to distance. So S dash frame has moved a distance vt ahead of the frame S along the x-axis. So see here, the S dash frame, which is moving with a constant velocity v along the x-axis, is a distance v into t times ahead of the frame S. So the coordinates of the point P in the two frames are now related as x dash is equal to x minus vt. The value of x is greater than x dash. So x dash is equal to x minus vt. What about the other coordinates? We have y dash is equal to y, z dash is equal to z, and t dash is equal to t. Now see, why is there a change in x coordinate and y and z coordinates have remained same? Because frame S dash is moving with a velocity, constant velocity v along the x-axis, therefore only its x coordinate changes, the y and the z coordinate do not change, they remain constant. So we get this equation that x dash is equal to x minus vt, but the y and z coordinates as well as the time coordinate, it has remained constant. Now, if we want to find the relation in the S frame, then we get x is equal to x dash plus vt. You can observe this from equation 1. This set of equation 1, you can observe from it that x is equal to x dash plus vt, y is equal to y dash, z is equal to z dash, and t is equal to t dash. Equation 1 and equation 2 both represents the Galilean transformation equation. And what is its significance? It relates the position and time coordinate in one frame of reference with the position and time coordinate in the another frame of reference. Now, if S moves with a constant velocity along x-axis, then x coordinate only varies, y and z coordinate, and time is remaining same. And if certain coordinate remains same, there is a new term or another term to describe such coordinates, and it is called invariant. This is a new term, invariant. Invariant means that particular parameter or coordinate remains same or constant. Now, see, suppose that there is a point P and the position vector of the point P in the S frame of reference is R, and the position vector of the same point P in the S dash frame of reference will be R dash. And we have seen that the frame S dash, which is moving with a constant velocity v along x-axis, is a distance vt ahead of S. Now we get a particular triangle. See this, observe this triangle. From here it is coming here, so to the point P, and then this is another vector. If you apply the triangle law of addition, then we get vt plus vector r dash. This is equal to r. So vt plus r dash is equal to r. Therefore, we get r dash is equal to r minus vt and t is equal to t dash. This relation is also called the Galilean transformation equation. Now, by triangle law of addition, we have seen that vt plus r dash is equal to r, and if we differentiate this equation 1 with respect to time t, and remember that v is the velocity, constant velocity with which the frame of reference S dash moves with respect to frame S. So if we differentiate it with respect to time t, we get the relation v plus dr dash upon dt is equal to dr upon dt. And if we make the substitution, what do we substitute? Dr dash upon dt is equal to u dash, and dr upon dt is equal to u. We get the relation 2, that is v plus u dash is equal to u, where u dash is the velocity of particle in frame S dash and u is the velocity of the particle in the frame S. So this is a relation which gives relation between the velocity in frame of reference S dash and frame S. And this relation v plus u dash is equal to u is called the Galilean transformation equation for velocity. It relates the velocity in one frame with the velocity in the another frame. Now what do we observe from this equation? That the velocity of a particle does not remain same in both the frames. In one frame it is u dash, in the another frame it is u dash plus v. So velocity of a particle does not remain constant, means it is not invariant in all frame of references in Galilean transformations. So velocity is different, velocity of a particle is different, and it changes as the frame of reference changes. Means the velocity is not invariant, it changes from one frame of reference to the another frame of reference. Now the Galilean transformation for velocity is v plus u dash is equal to u. V was the constant velocity with which the frame S dash moved with respect to frame S along x-axis. U dash is the velocity of particle in S dash frame and u is the velocity of particle in S frame. Now see, if we differentiate it again with respect to time t, now time derivative of velocity is acceleration. Since this v is constant, you get a 0 here and you get du dash upon dt is equal to du upon dt. So represent this du dash upon dt by a dash. What is this a dash? It is the acceleration of the particle in S dash frame. And what is this a? A is equal to du upon dt. It is the acceleration of the particle in S frame. So from equation 3, we observe that a dash is equal to a. Now what does equation 3 indicate? It shows that the acceleration of a particle in one frame of reference is equal to the acceleration of the particle in the another frame of reference. That is, the acceleration of a particle, it remains same in all the frame of references. In this case, we are having two frames S and S dash, and acceleration in S is equal to acceleration in frame S dash. Now acceleration of a particle remains same in all frame of reference, so we can conclude that acceleration of a particle is invariant. It does not change, it remains same in all the frame of references in Galilean transformations. Now acceleration of a particle is invariant in all frame of reference, so we can write a dash is equal to a, where a dash and a, they are acceleration of a particle in frame S dash and S respectively. Now if m is the mass of a particle and we multiply both the sides by the mass small m, and we know according to the Newton's second law, force is equal to mass into acceleration. So we get ma dash is equal to ma. If we represent this by force F dash and this by force F, then we get F dash is equal to F. This is our equation 4. And what is the physical significance of equation 4? It shows that the force acting on the particle in all frame of references remains same. So finally we can conclude that the force acting on the particle is invariant in all the frame of reference in Galilean transformations. So what we have seen in this lecture, the Galilean transformations that relate the coordinate in one frame of reference to another, and which parameters remain invariant under Galilean transformations. The velocity of a particle does not remain same in all frame of reference. It varies, but the acceleration of the particle and the force acting on the particle in all frame of references remain same. It is invariant in Galilean transformations. So that's all about Galilean transformation and the parameters that remain invariant in it. So have a nice day.